Hello, welcome to Lecture 4 in Chapter 3, Kinematics. In this lecture, we will look at freefall, specifically anything falling under the influence of gravity. So you can see here in the video, I have a bowling ball and a feather falling under the influence of the same gravitational field in a vacuum chamber. So if it's in a vacuum chamber, there will be no air resistance. So if you notice, right, you can see that, well, number one, they fall faster and faster, but also at the same time, they fall together in step and they will hit the box at the exact same time. Okay, so you can see it hits the exact same time. All right, so anything falling under the influence of gravity will come down, as mentioned there in these smiley faces of these scientists, NASA scientists, that it would fall and hit the ground at the same time because they are undergoing the same gravitational field influence. All right, so now we're going to show you a demonstration similarly conducted and recorded by Miss Ellie, and she will walk you through how to graph the motion of something in freefall.
Okay, so now we're going to look at a case study of what happens when you drop an object. I know we do this every day, right? We drop an object, but what is the physics behind it? How do we describe the motion? So here I have sent Miss Lee up the stairs in MCKL, and she's going to drop a tennis ball, and we're going to observe very carefully what happens to the ball in her hand. So let's pay close attention. Okay, we drop it. Pew, top, top. Wow, it goes down very fast. Can barely see anything. Let's try go a little more slowly. Okay, here. So the moment when the ball drops, she opens her hand and then the ball let goes. That's when the ball starts moving. It's at rest, right? So actually, that's the first fact we can write down. In the beginning, before anything happens, when you release the ball, that's what we call the initial velocity. So we say initial velocity, we always call it u equals 0. U means 0. Okay, so when it says drop from rest, that's what it means. Okay, let's see, continue what happened next. Okay, continue the video. Okay, it's going down faster and faster. You notice how fast it passes through all those lines on the background. Okay, and I rewind for you. It's going down faster and faster and then hits the floor. Okay, the moment when it hits the floor down there, that's what we call our final velocity. Okay, what do we use? Yes, we use v equals to some value lah. And this is usually the fastest it can be already. Ta-da! Okay, so this is how it's like the start and the end. But what happens in between there? Think about this. We say the ball gets faster and faster, but there's proper physics term for that. We say the ball accelerates down. So accelerates down. And in the absence of air resistance, you will have an acceleration of 9.81 meters per second squared. Now what is that? What is the acceleration now? Acceleration is the rate of change of velocity. Well, we can also write this as dv dt. Okay, rate of change of velocity. That means every second the ball is moving 9.81 seconds faster. What does that mean? Okay, I show you an example. Let's say in the initial velocity, t0, that's u0. The velocity is 0 lah. Okay, then 1 second later, what will the velocity be? Ta-da! The velocity will be 9.81 meter per second. How I know that, miss? Oh, ne? Acceleration is 9.81. So every second, you are 9.81 faster. So T2 is, guess what? V is, what's 9.81 times 2? My brain suddenly hang. 19.6. So that's what acceleration means. You just keep adding 9.81. And then you add again 9.81. And just keep going lah until you reach the final velocity, which will be, I say t equals to t. The v will be pretty fast by then. So every second you're going faster, and this is true if there is no air resistance. Okay, so how do we draw the graphs for this? Let's take a look. Now we come to the cannonball animation. Okay, we're going to use this to help us draw the graphs, the baby steps on how we draw that. Okay, so we have a cannonball. I'm going to fire a ball like just now. Okay, it drops down. You see the green arrow, right? It gets bigger and bigger. I replay for you. Green arrow gets bigger and bigger. That is what we call our velocity arrow. So if you want to draw a graph of velocity, it kind of looks like that. Okay, vt. We need to define our directions because in kinematics, velocity is a vector. So where is positive, where is negative? Okay, let's define. So let's define down as negative. How about that? Okay. Well, it's kind of normal, I know, like axis when you draw a graph, up is positive, down is negative. So first step, we need to define. So if this thing is moving down, getting faster and faster means it's something like this. Down, getting faster and faster, and this is supposed to be a straight line lah, okay? And as we have remembered earlier, the area under this graph means what? So the area under this velocity graph will be the displacement. How far has the ball traveled? Okay, so for this cannon picture, it will be from the top right here all the way to the bottom, height h, or displacement s, whatever you want to call it. And you can also draw a graph for the displacement with respect to time. If I define my ground down here as s0, then up here will be at some height, s equals to h. So I start at some height, h. And from there, I will do what? I will slowly go down, and then hit the floor. Actually, to be accurate, I should also match the other velocity graph down there. Okay, like that. Okay, there. So that is how we can draw our displacement graph. But one more thing we want to know is acceleration, right? We talked about acceleration. So acceleration is the gradient of a velocity curve, rate of change. Remember, we just said rate of change. So our gradient of this straight line is also acceleration, is also what we call this dv dt. So how are we going to draw this? You see our velocity graph, right? It has a constant gradient. It's a straight line constant gradient. And it's going down. So that's a negative gradient. So constant negative gradient is like this. What's the value? Negative 9.81. I draw on the man already. Okay, so these are the three graphs you want to think about. Start with the velocity in the middle. Then think about displacement. And think about gradient, which is the acceleration. And that's how I can think of something when you drop it from a high place.
Okay, you can find this in your page 3 notes. We are going to transfer the graphing. Okay, and the reason why this graphing is important is because it's commonly asked. You should know how to interpret graphs with no problem. Alright, so in your notes, right, we are actually going to study free fall and then free fall with rebound. So if you notice just now, when the ball hits the ground, when I let go of the ball rebounds a few times. So we are going to assume that there's no rebound first, and then we'll put it together later. So here you have a ball. I'm roughly trying to draw someone releasing a ball at a fixed height, a little bit like that cannon ball shooting the cannon downwards lah. So when he released the ball, the speed is 0, and you can see the V is increasing. Let's say it's V1, V2, and Vf is the final speed when it hits the ground. When the ball hits the ground, the speed is never 0, okay? And the reason why it will go faster and faster is because acceleration is also directed downwards, because the weight is directed downwards. This is called free fall, falling only under the influence of gravity. I'm going to now draw the S, the displacement, velocity, and acceleration graph, which Miss Ellie has mentioned just now, but I'm going to change it a bit. And I will take S equal to 0 as the floor. Okay? No, S equal to 0 is not the floor, it's where he released. Alright, so meaning this point is S equal to 0, where the ball is being released. So where you define your 0 point is really up to the question or up to the person doing the question. Okay, so just for a variety. Okay, so this is S, B, and A. It'll be useful if you sketch along in your notes as well. So from here, you can see that at first when I release the ball, so the easiest one to draw, right, is the acceleration, because it's always constant, alright? And then velocity will increase at a constant rate. It's going to be a straight line. Start from 0 because when you release the ball, speed is 0. This will be a curve, increasing negative value, increasing negative gradient. Okay, so let's say this is negative h because the ball is below the initial starting position. This will be negative g, and if you want to find the speed, you can calculate lah if you know how long the ball has fallen. So the time of flight here, I will label it as t lor. So if let's say you list down your STUVA, right? Remember I talked about sign. All these things are vector, so you should take note of the sign. Like the ball is below the original position, so negative h. Okay, and the g is downward, so negative g.
Now let's level up a bit. What if you throw something up and then... Now let's level up a bit. What if you throw something up and then it come down? Oh, will there be any different? Let's take a look. So here I'm going to throw a ball up. It goes whoop to the top, stops and comes down. Well, that's a bit fast. Let's go slow-mo a bit. I want you to pay close attention to where the ball stops moving. Does the ball stop moving? It go up, 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 and then come down, down, down. Check very carefully. Where is the maximum height? Where does it stop moving? Okay, let's go round 2. Goes up. And did it stop moving? Oh, it stops there. Okay, so this is our maximum height. Draw a line there. Then it starts to come down already. And it's getting down faster, faster. This part is like the one we look at, free fall coming down. Wow, okay. So there are some facts I want to point out to you before we go to the graphs. The first thing is, now you start off at the bottom. Oh, so your initial velocity is upwards. Now, how we have to define our things, right? So we define up as positive. You can define other way if you want. Down as negative. So we don't confuse our signs. So up is not going to be 0 anymore. Our initial velocity, because of my hand, I throw it up. And then you will have a starting initial velocity. But there's no force from my hand, okay? So initial velocity, this one is the maximum value. It's very fast. Okay, see if I can rewind to there. Give me a moment. There. Here. Ne? Okay, so the moment it leaves my hand, this ball is considered in free fall if no air resistance already. Okay, so it goes up, 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 up. Hits the maximum. Oh yeah, I cannot reach. Very slow. My hand not fast enough to click. Up and then hit the maximum point. Hey. So maximum points now we saw it goes up there, right? So this is where the ball actually stops moving. This is the maximum height. Or maximum point lah. At this maximum point, so the turning point, I guess you could say that, your velocity is 0. It stops moving. Because it's going to U-turn and come down. No more energy anymore. Okay, you look carefully again last time. Okay, I show you. Goes up, stop, come down. Okay, we wait for the slow motion to come out again. Where is the slow motion? Alright, watch carefully. This is very important because students always confuse this. You have to stop moving first. 0. Change direction. And now you're going down. Oh, that's interesting. Okay, so our definition is, we define up as positive. Okay, so this is positive U at the beginning. Then stop moving again, okay. Then what happens next? You come down. So I use different color Okay, come down. Now this sequence is now negative already because you're going down. And you're getting faster and faster as you come down. Okay, just now was going up, but getting slower and slower as you go up. Why is that? That's because of acceleration. So no matter where you are in this whole journey, flying up, flying down, your acceleration is still down by 9.81 meter per second square. So if you're going up slower, you're getting slower 9.81 meter per second each second. So every second you are about like 9.8 slower until you get to 0. Then after that you U-turn. Okay, so go up. U-turn come down, they're getting faster, yes. But faster by 9.81 meter per second each second. That's what acceleration is. Okay, so acceleration, no matter you go up or down, acceleration is still downwards. Okay, now let's look at the graphs. How do you plot the graphs of velocity, acceleration, and displacement for something you throw up and come down? Okay, let's start with the velocity graph, like I always say. So here is how it looks like, the yellow line. If you are wondering how we get the yellow line again, here, look at animation. Object is thrown up. Okay, so you see this object on the left goes up, but getting slower and slower. Alright, so like we said just now, getting slower and slower, but positive. That is why we draw the graph like this. See, this part is in the positive velocity. So it's going up, moving up, I should say, but it's getting slower because of acceleration that is downwards. So it's decelerating, you could say that. Moving up, but getting slower. Then you come to this point where velocity is 0. Where did we say velocity is 0? Maximum height. So this point is where velocity is 0, which is where the ball reaches the highest point it can go. This is all if no air resistance. What happens after that? Okay, let's continue the picture. So after that, the things are coming down faster and faster, and then hit the floor again. So here in this part, let's change color. It is moving down. How we know down? You look, -10, -20. So negative means moving down, we define that. And it's getting faster and faster. From 10 become 20. Wow. Okay, so we define up positive, down negative. Usually that's the point. That's the case. Right, so remember how to understand this graph. Okay, and as we mentioned, how does acceleration and displacement relate to this? Acceleration is the gradient. So gradient is acceleration, which is 9.81. Except that now we say, oh, actually down is negative, right? We probably should put a negative 9.81. Negative gradient, you see the slope slant down like that. Okay, so gradient is A, which is also your dv dt, which is gradient 9.81. Same thing. Okay, so if you see, the gradient is same all the way because straight line, so 9.81. Okay, and also your displacement, same thing, area under the curve. This part is how far it takes to go up. So go up to a certain height. Hey, sure. Then got another area when coming down. Same area when you're coming down. So you go up by that much, you must also come down by that much. Cannot suddenly ghost and then appear somewhere else. Okay, so there's area to go up, area to come down in green. Okay, so that's how you can understand your velocity graph. Now, acceleration graph, like we said, okay, you have the same acceleration everywhere in free fall if there's no air resistance. So if the object start to move up, it's still 9.81. Go down, it's still 9.81. Actually, this one say 10, but it should be 9.81. Okay, so it's just constant all the way, negative by the way. And that is your acceleration graph. What about displacement graph? Can we take a look at graph? Here we go. Okay, so displacement graph is a little bit curvy. We'll see why in a bit. Okay, so the object, as we throw it up, give it some initial velocity, it goes up, reaches a maximum height. So somewhere here, whatever this height is, and then it goes back down. So this system, we are defining this zero displacement as the ground. So it will go up to some height. I don't know what height is this. Okay, call this h. Looks like 10, 11 maybe. Okay, so here you're going up, coming down. This is like how you see it, go up, come down, go up, come down. But the question is, why is it curved? Well, there's this Stuva or kinematics equation called this. S equals to ut plus half at square. How does this relate to the graph? Okay, well, first if you think about this looks like a quadratic shape. So if we rearrange this a little bit, okay, S equals to ut plus half. Acceleration is negative 9.81, right? So we negative 9.81 t square. And you say, Miss, I don't see it. Okay, never mind, I rearrange for you. So in maths, we always say quadratic graphs. Y equals to negative, 9.1 divided by 2? 4.9, I think. 4.9 t square plus ut. Okay, so this is basically an upside down quadratic. That's why it's curved. Okay, and you notice the square is the thing that makes this displacement graph curve. But all in all, it's the same now. Okay, from bottom to top, this is your maximum height that it can go and come down. So learn to draw these three graphs for any kind of scenario. You need to stop and think, oh, displacement where? Oh, displacement up. Oh, positive. So go up, positive, if you define ground as 0. Okay, so that's how we can draw the three graphs. To summarize, here's another fun simulation we can look at. I have my cannonball again, and this time we are going to shoot it up vertically. So something like this. You see the green arrow? That's the velocity graph. So once again, velocity going up is getting smaller, coming down, getting bigger. So something like this. I cannot really see, not very clear. Okay, acceleration Notice the yellow arrow is just the same length all the way. That's telling us the acceleration is just going to be just downward all the way if there's no air resistance. Okay, why leh? Because you will see in the next chapter, what is this FG? That's gravitational force. We'll learn this more in chapter 4. But we have this gravitational acceleration of 9.81 because there's a gravitational force pulling it down. Now the rest is just showing you all the arrows already lah. Okay, so make sure you know how to draw the graphs, know the arrows, and how to use graphs to describe motion of some kind of object. That's all.
Okay, I'm here again to walk you through about the graph. So the reason why we emphasize the graph over and over again is because it's frequently asked, and if you really understand the graph, then it will help. You see, this is Miss Ellie. It's my drawing of Miss Ellie, look like Miss Ellie in the video. Okay, so you can see when she throws the tennis ball will slow down and then speed up. I kind of want to talk a little bit about what the slowing down and speeding up means, especially if you think about vectors. So if you look at the direction of G, right, when the ball is going up, the vector for velocity is pointing upwards, but the vector for acceleration is pointing downwards. That's why the ball slows down, because the ball is traveling up, but the gravity is pulling the ball down. So the ball is accelerating downwards. If they're opposite direction, it will slow down, okay, if you remember this. Then as the ball is on the way down, gravity and the velocity vector is in the same direction. That's why the ball here is speeding up. And of course, at the highest position, the velocity of the ball is 0. Okay, at maximum height. So if we're going to sketch the graph, once again, I will take ground as s equal to 0. And I'm just going to copy the axis of the graph lah. Okay, this is obviously sped up. So this is quite a good way to write your notes in one note, especially if you have a laptop or a tablet like me. Okay, a lot of things can copy one. So I'm just going to delete all these things very quickly. And just fast forward. So once again, you can see for acceleration, it is always equal to negative g. Okay, and let's say the time taken to fall to the ground is t. So the time taken to reach maximum height, which is the halfway point, will naturally be t over 2 lor. So I'm just going to mark t over 2 here. Okay, and this is at the highest maximum height. Alright, and at the maximum height, v is 0. Okay, all these are important points to think about lah. So as usual, the gradient of this line would be negative g. Okay, so that's why the velocity graph is pointing downwards, because in the first path, your velocity magnitude is becoming smaller and smaller because here you are slowing down. At the center, velocity is 0. When the ball is going down, velocity is negative, but the magnitude becomes larger and larger. Alright, so let us continue. That's why you get something like this more, and this will be v. By the way, u and v will have the same magnitude. Alright. Think about the equation. Okay, so now if you want to sketch, this is actually a quadratic curve, as Miss Ellie mentioned before just now. The quadratic curve, so the maximum height is here lor. But we can also check the gradient. If you look at the gradient, right, this gradient is in decreasing positive gradient. So your velocity here is decreasing positive v. This part here is increasing negative gradient, so this part here will be increasing negative velocity. Alright, hopefully that is clear. Okay, one last thing in this video that I want to talk about is actually how to use your kinematics equation, because we now know how to do the graphing. So when you talk about kinematics equation, generally, as usual, I would suggest STUVA. Okay, so let's say you want to find the maximum height. So when you list down your STUVA, the time taken to reach maximum height will be t over 2. The initial speed u is u, and then the final speed v is 0. Your a will be negative g. Okay, and let's say you want to find the time taken to fall back down, then your displacement will be 0 because you return back to the original point. Alright, etc, etc, because they can ask you to find so many other things. I can ask you to find, halfway, what is the velocity? After 3 seconds, what's the velocity? Alright, so try some questions. Okay, if you want, some examples might be posted up later, but try the questions in your task, and I will see you in the next video where this happens. You see, the ball goes boing, 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 boing. So we are going to talk about the rebounding and draw that graph. We will see you in that video. Take care now. Bye-bye.